In this video, I'm going to do an example where we show that the Taylor series for a function actually converges to that function for all values of x. So I'm going to do this for the Taylor series for e to the x. So I've written out its Taylor series, and let's show that e to the x actually equals this infinite polynomial for all values of x. And the idea is we're going to use the Taylor remainder formula. So we're going to use Taylor remainders. Okay, so when we use Taylor remainder on e to the x, what we do is we would approximate e to the x with a polynomial, with a Taylor polynomial, and that would look like 1 plus x squared over 2 factorial plus ... And let's say I'm doing an nth degree approximation. So I'd keep going until I get to x to the n over n factorial. So that is the nth order approximation for e to the x. But then I would have a remainder term. So the remainder term would be plus Rn of x. And now let's remind ourselves what the general formula for Rn of x is. So recall that Rn of x equals the n plus first derivative at some number c times x minus a to the n plus 1 over n plus 1 factorial. So this number c is some number that's in between x and a, inclusive. So it could be at one of those endpoints. Okay, so I'm going to bubble this. So this is just a brief review. What does that remainder look like? So if we were to plug in using our function, so our function is e to the x, if I let that be f, what we'd end up getting is that this n plus first derivative of e to the x is just going to be e to the x. And then if I plug c in, we'll get e to the c for that term. E to the c, and then a for our purposes is 0, because we're centering our series at 0. So we'd get times x to the n plus 1, and then over that n plus 1 factorial in the denominator. Okay, so that is what Rn of x for our function for e to the x is. Okay, so now what we want to do is we need to show that this remainder, when we take the limit of it, gets really, really small. It shrinks to 0. Okay, so I'm going to begin by setting up an inequality. So we know that when we take, sorry, let me write it like this first. I'm going to take the absolute value of this remainder, so the absolute value of Rn of x, and the absolute value of anything is always greater than or equal to 0. It's always non-negative. And if we take the absolute value of Rn of x, we're going to end up with e to the c, and I don't have to write that in an absolute value because e to the c is non-negative. So e to the c is already greater than 0. I don't need to put it in absolute value. But the x, I do. So x, I'll put that in an absolute value and to the n plus 1 power. And the denominator is non-negative, so I don't need an absolute value around that either. And we want to show this fraction converges to 0. Its limit is 0. Since that would imply that Rn of x, our remainder, goes to 0 as well. And that would be by, technically we'd be using the squeeze theorem. So Rn of x, its absolute value, is sort of squeezed by 0 on one side and this fraction on the other side. And 0, its limit is definitely going to be 0 because it's already a constant. So if we can show that this fraction also has a limit of 0, that would mean that Rn of x, its absolute value, will have the same limit by the squeeze theorem. Okay, so how do we show this? All right, so what I'm going to do now is consider two cases. I need to sort of deal with that e to the c term and figure out how we'll deal with that when we take this limit. Okay, so I'm going to draw a picture of the graph of e to the x. So the graph of e to the x looks something like this. Okay, and the y-intercept is 0, 1. Okay, and in the first case, so in case 1, let's say that this x is a positive number. So if x is greater than 0, what does that tell us? Well, if x is greater than 0, let's just put it somewhere here, somewhere to the right-hand side of 0. So a, the point that we're sort of centered at, is here. It's 0. And then c has to be a number that's between 0 and x. And it could be at either endpoint. Well, let me just put it somewhere. So let's say that's where c is. So in this picture, I can see that e to the c would be this y value, whereas, e to the x would be this y value. So in our picture, e to the c will be less than or equal to e to the x. And the reason why is since c is less than or equal to x. Because of that, e to the x is going to be larger than e to the c. Okay, well, what if x is negative? So that's going to be case 2. So if x is negative, so let me draw a picture. So I'll draw some axes again, and I will draw a graph. Actually, let me draw this a little bit bigger. You actually don't need that much below the x-axis, so I'm going to draw it more like this. Okay, so case 2 now. So case 2 is going to be, well, what if x is less than 0? If x is less than 0, then what happens? So if x is less than 0, it would be somewhere over here. Okay, and so e to the x would be whatever its y value is. C has to be somewhere between 0 and x, so let's say it's here. Its y value would be wherever this is, so e to the c. So what is e to the c now going to be less than or equal to? Well, for sure, it's going to be less than or equal to this y value at this point, the y-intercept. It's going to be, so the y-intercept is 0, 1. So we can definitely say when x is less than 0 that e to the c will be less than or equal to e to the 0, which is 1, since c is now less than or equal to 0. Okay, so overall, thus, what we can conclude about e to the c is that it will always be less than or equal to the maximum of what we got in case 1 and case 2. So in case 1, we got that e to the c is less than or equal to e to the x. In case 2, we got that e to the c is less than or equal to 1. So for sure, we can say that e to the c is less than or equal to the max of e to the x and 1. It'll be less than or equal to whichever is larger of those two. All right. So now, let's start. Well, so what I want to do now is, now we have a sense of how we can deal with e to the c. We know what it's less than or equal to. Now let's deal with the absolute value of x to the n plus 1 over n plus 1 factorial and think about, well, what's the limit of that going to be? So when we look at that x to the n plus 1 over n plus 1 factorial term, let's just write out some of the terms here. So on the top, you have absolute value of x multiplied by itself a bunch of times. So you have absolute value of x times another absolute value of x, and you could keep going like this. On the bottom, you have n plus 1 factorial. So you'd first have a 1 and then times a 2, and we'd keep going like this. Eventually, we get to absolute value of x over something. It's over something. I'm not sure exactly what's going to be in the middle, but if we keep on going, we'll have another absolute value of x over n, and then at the very end, we'll have absolute value of x over n plus 1. Okay. And the key idea is that these terms at the start may be big, depending on what x is, but when we take the limit, n gets really, really large. And as n gets really large, there's going to come a point in this product where some fraction in the middle, absolute value of x, over the something, this something is eventually going to get big enough where this is going to be less than 1/2, this fraction right here. And if that fraction is less than 1/2, everything after that is even smaller. So everything after that's going to be even smaller than 1/2. So everything here after a certain point, all of these will eventually be less than 1/2 for sufficiently large n. Sufficiently large n. Okay, so what that means is at the tail end of this, you are multiplying a bunch of numbers together that are really, really small. And as a result, this means that the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 factorial equals 0. All right, so now let's put this all together. So finally, what we get to say, if we think back to our inequalities, we had 0 is less than or equal to, I'm going to take the limit of everything. So the limit as n goes to infinity of the absolute value of Rn of x, that's going to be equal to the limit as n goes to infinity of e to the c times the absolute value of x to the n plus 1 over n plus 1 factorial. And this is going to be now less than or equal to, well, we know that e to the c, we know that this is less than or equal to the maximum of 1 and e to the x. We got that earlier in the video. And right now, for our purposes, I'm going to consider x as just being a fixed number. And if x is a fixed number, like the x doesn't depend on n, I'm going to move the limit past this, because this thing right here doesn't have any n in it. So I'll have this times the limit as n goes to infinity of, so what else is there? So we have the absolute value of x to the n plus 1 over n plus 1 factorial. I could only do this, I could only move that limit past this e to the c term once I know that e to the c term doesn't depend on this variable, doesn't depend on that n. Okay, so now we have this limit, but we know what this limit is. This limit is 0. And that means that when we multiply it by whatever that max is, whatever that number will end up being, that whole entire thing is going to be 0. Okay, so as a result, the limit as n goes to infinity of our remainder equals 0 for all x. And that's what we wanted to show. That shows that e to the x equals its Taylor series for every single value of x. So we can similarly do the same type of thing, for example, to show that sine of x actually equals its Taylor series for all values of x. And the same thing with cosine x. It equals its Taylor series for all values of x. We do it using this remainder formula. All right, so returning to our goals from section 10.9, we've now talked briefly about why and when Taylor series converge to the original function. And the argument centers around using the Taylor remainder formula.